Hello everybody. Today we're going to have a look at completing the square. Completing the square is a simple method of converting a quadratic equation in standard form to an equation in turning point form. So if we're going to explain that, we have a standard form equation. We want it to look like this, where the turning point would be negative PQ. We're going to start with monic equations where a equals 1. So one bit of information that's handy is to know the expansion of the square of a sum. So x plus a all squared always equals x squared plus 2ax plus a squared. And if we look at this backwards, x squared plus 2ax plus a squared, the coefficient of the x term is always half of what's in the bracket. Now we can use that to find equations in turning point form. So if we have a look at this equation here, x squared plus 2x plus 4, it's pretty close to the expansion for x plus 1 all squared. It'll have the same x squared term, it'll have the same coefficient of x, it just won't have the same constant. So in actual fact, x plus 1 all squared is x squared plus 2x plus 1. But if we wanted 4, all we'd have to do is add 3 to both sides. So if I add 3 to this side, I'll get x squared plus 2x plus 4. And by adding 3 to this side, we have to also add 3 to this side, and all of a sudden we've found the equivalent equation in turning point form of our standard form equation. Here's a second case. If we have x squared plus 5x plus 3, similarly, if we take half of the second term and place it here, we get an equation that's very close to what we actually want. But instead of getting 3, we've got 25 on 4. But using the same logic, 3 is just 12 on 4. So to get from 25 on 4 to 12 on 4, we subtract 13 on 4 from both sides. And lo and behold, again, we've got the equation in turning point form. Now, the only problem with this method is it looks a bit clumsy because we've got this not equals to at the top here. So if we want to get rid of that, we can modify our approach slightly and do it in one step. So similarly, we have x squared plus 2x, we have x plus 1 as per before, where this term here is half of this term. Now, we know we're going to end up with x squared plus 2x plus 1. So if we subtract that 1 off, we'll end up with x squared plus 2x, and then all we have to do is add 4 to both sides again. So negative 1 plus 4 will give us plus 3, just like we did up here. So square this term, subtract what was over here, and you do the equivalent of what we did before, but in fewer steps. Similarly, if we have x squared plus 5x plus 3, take this term, halve it, take this term, square it, subtract it, add the constant from before, simplify, and we get to the same answer we had before. Now, once you've mastered this technique, and it doesn't actually take very long, you can use this to find the features of a graph. So features of a graph would be the line of symmetry, the turning point, x-intercepts, y-intercepts, maximum and minima, the concavity, and the shape. So if we look at our first little graph here, y equals x squared plus 2x plus 4, and we found out before x plus 1 all squared plus 3 was the equivalent equation in turning point form. We can look at this and instantly know that the line of symmetry is x equals negative 1, that the turning point's at negative 1, 3, that the y-intercept is at 4. We could find it out from the turning point form equation if we wanted to by substituting in x equals 0. 0 plus 1 would be 1, all squared plus 3 would be 4. That's where that comes from. Because the coefficient of x squared is greater than 0, we know it's going to be concave up. The shape's going to be a parabola because the order's 2. The minimum will be at negative 1, 3. We know that from the concavity and the turning point. And we know that it has no roots because the lowest value of y on this entire graph will be 3. And for it to cross the y-axis, or at least touch it, it would have to be 0 or less. But let's have a look at a case where there are some roots and how we could possibly find that out from turning point form. Here's our x squared plus 5x plus 3 equation again, and here's the turning point form that we discovered. And again, we can find all the different features, but now we do have roots because the graph the minimum is below the x-axis and it's concave up. So we know that the roots are going to be when y is 0. Here's one here and here's one here. We just have to find out where they are. So to find that, we can use the turning point equation and substitute in 0 for y, which is what I've done here. I've just flipped the sides over, added 13 on 4 to both sides, took the square root of both sides, remembering there's 2 solutions, and then subtracted 5 on 2. Let's make this a bit clearer. And I find that one solution is at negative 5 plus 13, root 13 on 2, which is negative 5 on 2 plus root 13 on 2, and negative 5 on 2 take root 13 on 2, and thus I found the 2 roots of my equation. Now, all of this can seem quite daunting at the beginning, but once you've done it 4 or 5 times, it becomes fairly straightforward. And I hope that was helpful. Thank you, everyone.